for cosmic alchemy, the formation of some of the heaviest elements in the universe. During these collisions, atomic nuclei rapidly accumulate neutrons to form gold, silver, platinum, and other precious metals that eventually find their way into planets like Earth. Every piece of gold jewelry you own likely originated in such a violent cosmic merger billions of years ago. In some cases, short bursts may also result from a neutron star merging with an existing black hole. The energy scale of these cosmic explosions challenges human comprehension. A typical burst releases more energy in a few seconds than our entire sun will emit during its 10 billion year existence. An output so massive that converting Earth's entire mass perfectly into energy would still fall short of the most powerful bursts observed. These bursts aren't omnidirectional, but produce focused beams that slice through the cosmos like celestial spotlights. This directionality explains why we detect only a fraction of all gamma-ray bursts. We only see those where the beam points toward Earth. The focused nature also explains their destructive potential. When a burst points directly at a planet, it concentrates its energy rather than dispersing it equally, potentially affecting worlds that lie in its path. Scientists estimate gamma-ray bursts occur approximately once per day across the observable universe, mostly in distant galaxies billions of light years away. Their tremendous brightness allows detection even at these extreme distances, making them valuable cosmic beacons for understanding the early universe. The detection of these events represents a triumph of modern astronomy. Gamma rays don't penetrate Earth's atmosphere, so their discovery awaited the space age when detectors could be placed above our protective shield. The first bursts were actually discovered accidentally by satellites monitoring nuclear test ban treaties in the 1960s. Scientists initially considered possibilities like alien civilizations or secret nuclear tests before discovering the truth. Gamma-ray bursts represent the most energetic electromagnetic events since the Big Bang itself. Supernovae, solar flares, even active galactic phases, none compare to the raw power of a gamma-ray burst at its peak. This enormous energy output creates an intriguing possibility. These bursts might be visible across much of the observable universe. Some scientists suggest advanced civilizations might harness artificial gamma-ray bursts as beacons to announce their presence across intergalactic distances. But for life-bearing planets, these cosmic lighthouses represent potential extinction events. Their energy can strip away protective atmospheric layers and bathe planetary surfaces in lethal radiation, especially if a burst occurs relatively nearby, with its beam pointing directly at an unfortunate world. Research continues to yield new insights. Recent observations have identified ultra-long bursts lasting hours instead of seconds, suggesting additional creation mechanisms we don't yet understand. Others have shown evidence of gravitational waves accompanying short bursts, confirming their origin in neutron star mergers and opening new avenues for multi-messenger astronomy. Atmospheric assault: how gamma rays attack Earth's shield. What stands between us and the harsh radiation of space? A fragile layer of ozone, just a few millimeters thick if compressed to sea level pressure. When a gamma ray burst strikes this delicate shield, it triggers a cascade of atmospheric chemistry that transforms our protection into vulnerability. Unlike many cosmic threats that directly impact Earth's surface, gamma ray bursts wage their assault through more subtle means. The gamma rays themselves don't penetrate to ground level. Instead, they unleash their destructive potential by fundamentally altering our atmosphere's protective chemistry. This invisible attack makes GRBs particularly insidious, as their most devastating effects unfold through a series of atmospheric chain reactions. The ozone layer, our thin atmospheric armor, absorbs the majority of the sun's harmful ultraviolet radiation before it can reach the surface. This slender shield of triatomic oxygen molecules protects all terrestrial life from DNA-damaging radiation. Without it, life as we know it couldn't exist on land. But this protective veil becomes surprisingly vulnerable when confronted with a gamma ray assault. When gamma rays penetrate our upper atmosphere, They immediately ionize atmospheric gases, splitting apart nitrogen and oxygen molecules. This splitting creates nitrogen oxides that act as catalysts, systematically dismantling our ozone shield molecule by molecule. Each nitrogen oxide can destroy thousands of ozone molecules before being removed from the atmosphere, a devastatingly efficient process. The scale of potential destruction is sobering. Models indicate that a mere 10-second exposure to a nearby gamma-ray burst could deplete up to 75% of the ozone layer in regions directly exposed to the radiation. Global ozone levels could drop by as much as 38%, creating a worldwide crisis far exceeding any atmospheric damage humans have ever caused or witnessed. This depletion wouldn't manifest as a uniform thinning. Instead, it would create dangerous holes in our protective shield, similar in concept to the Antarctic ozone hole from chlorofluorocarbons, but potentially far more extensive. Through these atmospheric wounds, harmful ultraviolet radiation would flood onto Earth's surface at levels life hasn't experienced since before the ozone layer formed. The geographic distribution adds another layer of complexity. When gamma radiation enters the atmosphere over a polar region, the depletion becomes concentrated there rather than spreading uniformly. This occurs because the radiation produces chemical changes primarily in the middle atmosphere, and atmospheric transport flows predominantly toward the pole. Consequently, polar regions could experience even more extreme ozone destruction than global averages suggest. Our atmosphere wouldn't remain compromised permanently. Models suggest the ozone layer would gradually recover over approximately 5 to 7 years. During this recovery, ozone in the lower atmosphere might measure around just 10 parts per billion, varying seasonally. Imagine stepping outside into a sun that burns without mercy day after day for years, a world where shadows become sanctuaries and exposed skin blisters within minutes. The severity depends largely on the fluence of the burst, essentially the total energy delivered per unit area. A more energetic burst, or one directed more precisely at Earth, would cause greater atmospheric disruption. Local ozone depletion in the worst affected regions could reach 74%, creating areas where almost no protection remains against the sun's ultraviolet radiation. Visualize our atmosphere as a complex chemical factory with carefully balanced production lines. Gamma rays sabotage key workstations, causing harmful compounds to form while shutting down protective processes. The factory doesn't explode, it begins manufacturing the very chemicals that slowly dismantle its protective systems. This atmospheric damage represents a fundamental difference from other extinction-level threats. An asteroid impact or supervolcano eruption would affect our atmosphere primarily through dust and debris that eventually settle. The chemical changes triggered by gamma-ray burst would be more persistent, altering atmospheric chemistry for years after the burst has passed. The atmospheric ozone we rely on daily exists through a delicate balance of formation and destruction. Oxygen molecules split by ultraviolet radiation from the sun allow individual oxygen atoms to combine with other oxygen molecules to form ozone. The gamma-ray burst shifts this equilibrium by introducing new destruction pathways that overwhelm the natural formation processes. Our modern understanding comes from sophisticated atmospheric models combining astrophysics with atmospheric chemistry. These reveal that even a relatively distant GRB could trigger significant ozone depletion if Earth happens to be in the path of its narrow beam of radiation. Perhaps most concerning is how quickly this transformation would occur. Unlike climate change or other gradual atmospheric alterations, the chemical reactions initiated by a gamma-ray burst would begin immediately and accelerate rapidly. Within days, significant ozone depletion would already be underway. Ecosystems would have little time to adapt as the sky itself becomes a threat. This atmospheric assault would ultimately transform Earth's surface environment through the flood of solar ultraviolet radiation penetrating the compromised ozone layer. UVB radiation, causing sunburns and DNA damage, would increase dramatically. The more energetic UVC radiation, normally completely blocked by our atmosphere, might reach the surface in measurable amounts for the first time in Earth's recent history, bathing the planet in radiation hostile to the very foundation of life. Extinction